say some things.
Okay.
Okay, well, let's see. For people who are joining this live stream, I signed myself up to try and talk a little bit about how to write expositions as computational essays. And we have several people here who have written lots of stuff. And I've written lots of stuff myself. And I think what I signed up to do was to maybe critique some of what some other people have written. And I think the last time we tried to do one of these, not as a live stream, and I realized I was doing a terrible critique of things that were written by somebody now. And I thought, at the very least, let me go and critique things that I myself wrote a long time ago. So I found stuff on the web that I wrote when I was like 12 or 13 years old. And we could critique some of that. It was kind of fun to critique. But maybe we should go to, that was before computational essays. They would not be invented for another few decades after that. All right, let's go and look at some of the things that have been provided here. All right, let me see. So we have one about Fourier series. See, Eric is an experienced writer here. I'm not sure that this is going to be as useful as, I think I looked at this one before, didn't I? Has this been changed since the last time or not?
Not much on that section, no.
Okay, so I'm going to critique this immediately. I mean, well, I think you changed a bunch of things here, but the first point is, like, what on earth are we talking about here? Right? You've got to have some introduction that just is saying, I mean, it's good to jump into this. Yeah, you see, you got to show here for the typical person. Okay, unfortunately, it's a little bit tricky, right? I mean, you got to show this. How do you show this? You would say, see, this is kind of ugly to have to do something like this. Oh gosh. No, I'm sorry. This is, look, what you should start with is just to say, we are going to look at what happens when you nestedly apply a function. Okay, and then we've got a particular function. Let's consider when, and maybe even, although I hate to say it, you say f of x blank colon equals this thing might be useful, but you've got multiple kind of conceptual things going on with the width here. Why do you have the width here? You don't need the width here. You can just say, just get rid of the width and just say 1.5 here. And just say, what does that do? Okay. You don't, well, okay, you can say it approaches 0.3. All right, fine. That's pretty obvious what's going to happen there, but it's okay to show that. Oh, I'm sorry, it's very small. Yes. You see, there's more drama here. The fact that it does something really wild here is drama. There's, if I was writing this, what I would do is I would have some kind of build-up here of, oh, it goes to a fixed point. Okay, fine. In fact, my first example might be having it go to a limit cycle, just because that's not hard to understand, but yet it's a bit more exciting. It's like, well, somebody might look at this and they might say, it's obvious any iteration of a function must go to a fixed point. Am I making sense?
The one part I wouldn't like in this moment is that we mix mathematics with numerics, with machine numerics. And the normal person has no intuition which is which.
That's true too. I mean, you've got to, one challenge here is, can people understand this idea of nesting functions? I suppose, I don't know how intuitive that is. That's certainly, I mean, certainly when I show that particular thing, you can do something like this. Oops, you can do something like this. But I'm not sure that really helps, because then going from that I think that's actually super confusing then, probably, to go from that making a frame around something to doing something with a numerical value. I mean, what was your point, Michael? That people that going from something like this to going to something with numbers was confusing?
No, my point is, like, you show here a list of numbers. They are correct. If the list would be 10 elements more, they would be wrong, because we mix machine arithmetic with mathematics.
Sure. See, that's in a category. I mean, I have certain principles of expositional writing. As people who've worked with me have heard before, my 0th principle of expositional writing is that if you don't understand what you're writing about, your readers don't stand a chance. This is another principle, which is you've got to know several, a significant distance ahead of what you're of the exposition level you're trying to achieve. In other words, when somebody writes something, if I'm trying to explain something, I know when I'm getting close to the limit of what I understand, so to speak. And one has to be sort of super careful there. And so in a case like this, eliding the point that Michael is making about machine precision versus arbitrary precision and so on, just not having to address that question is a good thing. But understanding that there is such an elephant lurking in the corner of the room is important. I mean, in other words, if you were a place where I always get nervous writing expositional things is when I know I'm very close to the edge of what I understand. Because if you're close to the edge of what you understand, it's very easy to end up saying something that is technically wrong, so to speak, because there was something from just over the divide of what you don't understand that is going to come and bite you. Whereas if you're still far within what you understand, you can be pretty sure that even though you say things informally, it's like people are obsessed sometimes with, when they write expositions, they're obsessed with, you can't say centrifugal force, let's say. Really? Why not? Long explanation about some formal thing about definition of force, et cetera, et cetera, et cetera. That's perhaps a bad example. But, it's like, don't worry, I'm not going to get myself in trouble because I do think I understand the bigger picture of what's going on. And it's people sometimes get obsessed with this, you've got to say the precise thing because but so long as you understand a fair distance beyond the exposition you're giving, it's not really such a problem because you can make sure that nothing you say, so there's some things where you could say it, and then because you made that imprecise statement, you tangle yourself up in some other issue, and then you're kind of toast. But if you kind of know what you're doing, you can avoid that. Yeah, so I see on our live stream is commenting that every computational essay would start with the central result. I agree. Giving people a roadmap of where you're going is very important. Like, for example, let's take Fourier series. Okay, so I'm going to criticize this. Sorry, Eric. Is Eric here?
Yeah, I gave you more than I knew you wanted so that you can throw some out.
Okay, well, here, okay. The question is, who is the audience here? So if I was going to explain Fourier series, so the question is, at what level is the person you're explaining it to? By the time they understand orthogonality relationships, they probably already know about Fourier series. And this is, by the time they understand orthogonality of functions, Fourier series are example number 1 of that. So even using that word kind of already zeroes out your audience. Because, now there's a different, there's a different use for documents which are refresher documents. That is, the person, for me, sometimes I'll be like, I more or less understand this, but I need a refresher on what the definition is. That's a somewhat different thing. But so let's talk about how would we explain Fourier series and who is our audience. So let's say, okay, we can assume that if we're going to explain Fourier series with formulas and all that kind of thing, that, okay, so let's assume we're heading for I don't know the school system well enough, but maybe the pre-calculus crowd. Okay, so okay, first question is, do they know trigonometry? Do they know what sines and cosines are? Okay, one question is, can we get there from here? If they don't know what sines and cosines are, can we still explain Fourier series, or are we up a creek without a paddle? What do people think?
My question would be, why would we want to do this? I feel like the audience that has heard this or is currently studying it is probably a much more attentive audience than an audience for which this is 4 years in the future.
Fair point. Okay, so let me make another point.
The question at the beginning, who is the audience? And I think we're still answering that question.
Right, but I want to address what Michael is saying, okay? So, you know, there's ways people understand things, right? And some people are better at buffering non-understanding than others. For example, I'm not very good at that. If I'm trying to understand something and there's a step that I just don't get, it's very hard for me to go on past that. And I mean, I can, you know, sometimes I can go on past that as sort of intuitive, swinging through the upper levels of the jungle type level. But if I really want to, you know, really understand it and be able to reason about it, if there's a step I don't understand, I'm toast at that point. Other people have an easier time getting through things where there's parts they don't understand. And I think, you know, one of the things that Eric did with MathWorld, then copied by Wikipedia and so on, is this kind of, you know, tell it as it is, which I think, you know, sort of very direct writing, which people had tended not to do for things like math before that. And so now that I'm criticizing Eric here, but no, what am I trying to say? The thing I'm trying to say in response to Michael is, yes, you're right that the people who are really studying Fourier series will understand more stuff. But what if they manage to get through? I mean, this is the thing. You talk to people, they say, I did my calculus class. I got an A in my calculus class. Oh, can you understand what, you know, a function of a function is? You know, so in other words, they didn't get it. They thought they got it to the point where they could get an A in the class. I was just seeing something yesterday talking about the sort of the number sense and whether humans are unique among animals in understanding the idea of numbers. And the point was being made that, yes, you can teach a chimpanzee to go point at things, but that doesn't mean that they necessarily have the idea of numbers, so to speak. And I think, you know, this is the question. I tend to feel like the extent to which you can go back to basics and explain things from something very, very basic is worthwhile. Now, some people, you know, a phenomenon that I think has changed over the years is if this started off with something that seems like it's a very basic explanation of what sine and cosine are, you might say that's going to lose a big part of the market because people are going to say this is too elementary. Well, if they can visually look ahead and see it's got formulas and things like that in it, then, well, I mean, yeah, you're right. I mean, it's hopeless. If you can't explain, you know, you're right. This is not explainable at the, you know, at the pre-calculus level, probably. It's probably by the time you've got integrals for the orthogonality of the functions, it's not explainable. So, you know, but let's see what.
But one thing.
Go ahead.
You know, I think that there are many explanatory models and people learn differently. Some are visual learners, some are verbal learners, you know, and some get motivated by applications or uses. Yeah. And I think that just opens up the space of what the computational essay can capture. There are different paths to learning and motivation. I think motivation is key, for instance.
Yeah, but you see, okay, so here, right.
So I think that one can criticize it, but I think that there's sort of different paths to learning.
Yeah, but this isn't a computational essay. This is just a math statement here. This isn't, you know, the computational essay version of this would be, let's look at, you know, let's plot. I mean, the computational essay kind of discover it as you go version would be, I mean, here you're just, you know, you're announcing the mathematics, basically. You know,
So
go
the
ahead.
competitions you want are in the subsequent sections. So this is more kind of lay out what you're going to do and then show how to do it. Whereas what you're describing is do it as you're explaining it.
Right. I mean, I think, you know, so here's a challenge. Can you explain why sine x and sine 2x are orthogonal? Well, I bet you can. I bet if I say filling arrow, whatever, axis here, I bet that I can see if I plot sine 2x and I look at the product of those two things, right? I see those two and I look at the product, sine x times sine 2x. And then I bet that you can see that, by golly, the integral of that is 0. See what I'm saying? Now, you know, maybe that's not, I mean, to me, that will be a useful way to show people, you know, rather than them having to work out the integral by hand and say, oh yeah, it works out that way. You can just, in fact, I've never tried this before. This is kind of a cool thing. I didn't really know, you know, look at this. You can actually see, wowee, look at that. If we mark these off in 2 pi's, let's take a look at this. Isn't that cool? I mean, I'm sure you guys all knew this. I didn't know. I mean, I didn't know you could, you know, this is showing, right? The integral of that is 0. And I don't know, everybody is either speechless or doesn't agree with me.
Is it because you already know the
I would
answer?
say, like the Mythbusters say, it's plausible.
Yeah. It's hand waving.
Yeah, I think
But
that.
what's your point? Your point is, okay, the question is, okay, so then we can do something where we say sine 2x times sine 3x.
No, it's beautiful, Stephen. But I say it's not a proof. It's plausible.
I know that, but this is the point. You're trying to get people to understand. So here, for example, I don't ever know which it is. Is it trig reduce? Is it trig expand? Okay. So this here is looking better because when we do this, we can see that, you know, the integral over 2 pi is going to be 0 there. Where am I putting this? So, I mean, you know, again, and that's a more elementary thing than doing these integrals, probably. I don't know. I don't even know how to do that trig expansion anymore. I only know how to do it in terms of e to the ix and so on. But you know, so, I mean, in terms of these Fourier series, you know, what I would say is let's start off from some, you know, what I would do if I was doing this was I would say, you know, I don't know what the Fourier series for, what is the Fourier series? Kind of, how do I work this out? Fourier series, I'm going to do a square wave. Fourier sine series, how do I do this? Square wave of x, let's say x0 to, do I do it this way? How do I do Fourier sine? Roger, somebody else?
Yeah, I mean, yes, but you probably
terms.
want square wave of pi x or some such, because that's going to have period 1 and the trigs of period 2 pi and things like that.
Okay, all right, okay, so what's taking all this time? What's it doing?
It's probably computing it.
Why is it hard? Isn't it just some straightforward sum of, what is all that garbage? What is all that garbage? Is this going to take it forever too? I mean, I know this is a simple Fourier series. Ah, is there a Fourier n?
No.
Well, I don't know. Anyway, okay, so let's just take this and let's take the first, you know, 3 terms of that and so on.
You sure you don't want to scroll down the computational essay where?
I think you want, you know, square wave x over 2 pi, because then it matches nicely.
Yes.
Okay.
You want the lengths to be coincident.
Yeah.
Okay, let's take a look. Eric has already done this.
There you go. There's your triangle wave or square wave or whatever.
Yeah, well, this isn't bad. I mean, again, this is interesting. This looks pretty good. There we go. Finally, the square wave.
I think that has the coolest plot at the very bottom, with a good idea from Michael.
Which one?
That one.
What the heck is it?
That's the Gibbs phenomenon.
Yeah, nice.
Oh, that's nice.
That made continuous.
For continuous n.
Yep.
That's very nice. Wow. Never seen that before.
As usual, Michael has good ideas.
That's why I wouldn't start with a function that is discontinuous, because this adds a whole bunch of complications into the theory.
Fair point. I mean, to me, it's super useful to say, here's where we're going. We are trying to, okay, here's what I would do. I would say, this is a story of approximating, functions by sums of sine functions. Okay? Why do we care? An example of a reason why we care is because, the math version of it is the sine functions, the eigenfunctions of various operators, but we can say that more, that if we decompose things into those, then it's easy to tell what happens, because it's easy to tell what happens to each of those functions type thing. In other words, that's the plucked string version. But in other words, what else would we say? I mean, like decomposing into sine functions. Perhaps the other thing to say is, and it turns out to be very efficient to decompose things into sine functions, which is why they're used in, JPEGs or something like that. If it was incredibly slow to do that decomposition, they wouldn't be used there. So that's another, that is part of the preamble, fact, is that it could be decomposing. If I said to you, decompose this function into continued fraction of Bessel functions or something, you'd be like, I don't know how to do that. That's really hard. But the fact that Fourier series are useful is partly because it's tolerably easy to decompose things into Fourier series. Do you agree? Roger, Michael, anybody want to comment on that?
Yeah.
So at the beginning here, what I would be saying is, rather than giving a very formal definition, see, I mean, this is so off-putting to somebody who is, yes, if you're a math person, it's like, let F be a field with these properties, blah, 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 and you're off and running, but that's math, people. I mean, it's like, even...
Does it cover sequences? Because that's where it actually is easy. It's not so easy for functions. It's very easy for sequences. That's where you have the fast Fourier transform.
Less useful in terms of you mean Fourier transforms?
Yeah,
but
Fourier transform and Fourier
Fourier
series are not cheap to compute. Discrete Fourier transforms are cheap.
Yes. Craig is commenting on our live stream that he's saying he usually starts by saying, how do we represent tides or heartbeats or other periodic phenomena? Yeah, I mean. So
that's appealing to applications, which I think is motivating. I think motivating.
Right. I mean, of course,
which
the
is
trouble with any of those applications is, okay, both tides and heartbeats. Well, the tides, for example, well, they're not as periodic as you think they might be. They have an 18-year period, roughly, right, or something. But it's a bit. I mean, that's a slightly see. This is one of the things I always find curious about explaining stuff, is like, I'm reminded of a silly story. Okay, I was looking years ago about some history project. I was looking at for video footage of John von Neumann. Okay, and there is, at least at the time, there was only one known piece of video footage of him, which is him being on a television show with a very 1950s title of something like Youth Wants to Know, okay? And it's like, and you know, he's being introduced as some, you know, member of the Atomic Energy Commission and so on. He's got some device there, and some kid is asking about this device, and it's like the device is all kinds of pieces and so on. And turns out the thing the kid really points to is the carrying case for the device, right? And so John von Neumann rather charmingly explains, oh, that's just the carrying case. But the whole point is, when you try and show people things, what's the carrying case and what's the actual thing? See what I'm saying? Like if I said, this is the tides, let's say, well, the periodicity of the tides is complicated. I mean, if we go and look, I'm sure we can, you know, if we go and pull up your average, let's see, if we just go to Wolfram Alpha and we say, you know, something like, you know, tides in New York Harbor. And we say more days. And it's like, you know, hello periodic function. It's sort of periodic. Well, actually, it looks more periodic than I remembered it. But I mean, I don't know whether it's always that. I don't think it is always that periodic. I think there are plenty of places where it looks a lot less periodic than that. But so again, this is my question. If you're showing something like this, if it's just tough, because it's like, when you start explaining that, it gets a little kind of, you know, what are you supposed to notice? What are you not supposed to notice? Did this make any sense to anybody? I mean, I think that
you're trying to teach the way you learn, which is developing an intuition. And I think the way some of these computational essays have been presented is a start from a very low entry point, give all the basics like a textbook, and then add examples so that people can start. You're starting with the intuition side.
Craig here is saying that he has tide data from 2019 in Boston and asked students to find the dominant frequencies. You see, it's not fair, because I know, using meta information, that Craig is teaching MIT undergraduates, which is definitely already a very kind of selected set. And for them, that sounds like exactly the right level of thing to do. I mean, I think that
one thing that computational essays have an easy time doing is to explore examples and do intuition builders.
Yes.
And one thing that's hard when you have to manually do it is to do enough intuition builders. So one is in some sense data rich or example rich in a computational setting.
Right. By the way, Aaron on our live stream is commenting on the fact that he wants an analog of our function documentation where you can just sort of open up something about Fourier series and see a bunch of examples and just understand how to do them. I absolutely agree. That's what I mean, you know, and that's what we kind of all keep on saying, is that I mean, if we go, let's even go to the Fourier sine.
So I want to preamble that by saying that this is in the old style of book appendix documentation.
Fourier sine.
We are migrating these. I mean,
okay, give us an example that isn't, Roger.
Limit.
Okay, but I mean, even here, okay, even here, this is pretty good. It's like, I'm not totally clueless. Okay, T is a little confusing that it's T comma T. Okay, whatever. I wouldn't, you know, again, that's like a little confusing. But here, I've already got a lot of the points. You know, I'm writing it as some sum of signs, and it reproduces the result, but not exactly. That's a good start. But
I just want to say with a sentiment, it is our goal, and we are migrating pages from sort of computer manual pages to learning pages.
And how do I see that here, Roger?
Sorry?
What I mean, you mean in?
I mean, the examples then, you know, that there should then be sort of.
Oh, for God's sake, this is horrifying. This is just horrifying. I mean, that at the very least should be
that
iconized.
didn't exist at the time. There's 6,000 pages to go through and iconize.
Fair enough. But, you know, the reason that I'm objecting, and in terms of us talking about exposition, it's like, that's, you know, somebody was commenting on, you know, what's math, what's computeristic, and so on. That's a piece of pure computeristic random crud, right? I mean, that's not, I mean, I would also have argued that if you're really going to do it that way, you would be better off to say something like, you know, show this with, you know, graphics 0.01, and you know, the fact that we've got an actual point size
Graphics.
Thank you. Yeah, well, obviously that didn't work.
It's there.
I know it's there, but it didn't work in a nice way. IC is asking, is epilogue not recommended? No, it's not that there's anything wrong with epilogue. I'm just saying that conceptually, if I'm thinking about, I'm doing limits, I'm plotting functions, oh my God, we just dive deep into the entrails of the animal, so to speak, seeing all of these very computeristic, you know, epilogue sequencing of graphics type stuff. I think, but look, in terms of let's take the Fourier series example. I think we're all saying, I mean, even what to me, you know, maybe I'm wrong, but I think this is, you know, seeing this, I'm not so keen on the t comma t. That's a bit confusing. I mean, if I said t squared here, would I be toast? Yeah, it's a bit messy, but, and that's a little bit incomprehensible. Okay. And obviously what we've got to explain is this is representing things periodically, blah, blah, blah. It might be better to not plot it over this larger range. I don't know. I mean, again, this is the carrying case phenomenon, right? When you say t comma 5, it's like, what's what here? What am I supposed to be paying attention to? Is it important that those two things are the same? Is it, you get what I'm saying? Maybe I'm being unclear here, but I mean, you know, it's like there's a payload, and there's you know, there's the t that's representing the independent variable, and help me to distinguish those just by looking at this example. No comments.
Yeah, like 2t comma t.
Yeah, even just 2t comma t would help. Yes, that would help. And I mean, here, if we were explaining this for the first time, we might not want to do this. We might want to say, you know, 0 to 2 pi. I don't know what this is going to do if I do 0 to 2 pi. Oh, disaster. Well, whatever. I mean, and this is a case where you have to sort of understand a bit more than you know, it might take for me to find this example. I might spend a few minutes puttering around trying to find the example that is going to look reasonable here. And that's, you know, that is both going to have the constraint of being simple, being sort of payload distinguished from dependent variable, being whatever, to actually work. But I mean, to me, and look, the first point is that I might almost argue is, I mean, you know, what we're really talking about is how do you build up a function from sines and cosines? Okay, I think that's the main point. And one point that I think Craig is implicitly making is it's really all about periodic functions. And I suppose I'm eliding that point a bit, and maybe one shouldn't. Maybe one should just take that head on, that this is about periodic functions, and say, you know, I'm not sure, maybe, yes. Yeah, maybe it's right to think, I mean, again, that's another one of these expositional things is, yeah, I think it's probably right. I think you have to say it's about periodic functions. Otherwise it doesn't make a lot of sense. And you're going to get weird, confusing things like this, which is probably why we shouldn't use a function that isn't periodic here. Am I making sense? I don't know what the right, which means we're probably using triangle waves and things of that kind. But then, okay. look, in terms of the presentation of this, I mean, to me, as I think Roger is saying, other people are saying, the big new freedom that we have is we can quickly show an example. If you're writing a textbook, there's no choice but to do this, right? So if we scroll down here, why the heck are we talking about shifted Fourier series in section 2 here? We don't even know, we haven't even seen a single picture of anything. We're already talking about shifted Fourier series. Eric, explain yourself here.
I think
don't
it's
really
right because in most cases, as the examples mentioned earlier, like tides or heartbeat, heartbeat is not pi seconds, the tide is not pi days, it's some other unit. So we need one that doesn't go from pi to pi. We need one from generic L to minus L.
All right, this is another exposition principle, right? I mean, you know, what is obvious to people and what isn't? And, you know, we've learned that over the years in language design, lots of things where people immediately extrapolate and they don't get confused, and things where people get irreducibly confused. And, you know, I would argue, I don't know, you know, do you need this piece of scaffolding to not get confused? I don't know. I mean, or is it the case that you just elide it, you cheat, you make the first example be something where it so happens that everything lines up with, you know, pi, 2 pi periodicity. And then only later do you go back and say, oh, actually, you know, we can deal with any periodicity, so to speak.
So I can't speak for other people, but I can speak for myself as a physics student many years ago. This was exactly the point that tripped me up about Fourier series. And I wish that somebody had sort of done this right at the very get-go. So this is actually reflecting my own educational bias, in that if I would have understood this point, I would have got it right away instead of it taking me a while to figure out what was going on.
Well, okay, so this is always the challenge. So, you know, one of my expositional things, I always criticize British textbooks of various kinds. You know, there was a different style. I'm maybe not in the various people saying yes. I don't know what they're saying yes to. So that was perhaps the commenting on Eric's comments here. But you know, I was going to say British versus American textbooks back in the day. Probably they've normalized by now. The British textbooks were always full of trickery. Like I remember there was an electromagnetism book where every example it gave was a trick. That is, you could do it in this particular case because these functions decomposed in this way, blah, 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 blah. Whereas the corresponding American textbook in those days was, let's deal with this bigger industrial machine that is harder to understand, but will bash through all these different examples. And I have to say, you know, I'm advocating, you know, what I'm advocating is the trickery that isn't really trickery that is readily generalizable, so to speak. But okay, so people are agreeing that shifted Fourier series is an important concept.
Which doesn't mean that the normal Fourier series out of the box shouldn't be given a few examples in some amount of space up top. But the expense, of course, is the essay gets longer.
Well, okay, and the other problem is there's a point at which the student has already drowned. You know, they gave up. They're like, I'm not going to understand this. I drowned. And you know, I think you have to get to something that they can understand within a fairly short distance, or you're going to have that phenomenon. I mean, I think. You see, yeah, I mean, and this again, it's also a difference. You know, I know from dealing with groups of like kids and people, you know, high school kids and other things like that. You know, if you're in some group of kids and you're explaining something about language and you're giving examples and so on, and some kid asks some question about, you know, just tell me what the formal definition is. You know, structure, formal definition. You can pretty much say, and I have gone back and checked a few times, I can say, you are going to be a pure mathematician or something like that, because those are the only people who think that way. And sure enough, that's usually what happens. And, you know, so there are certain people who who think in terms of the formal definition and then work back down from that. Most do not. At least that's my anecdotal observation. I mean, most people find it easier. Some people say, given the structure, n is an element of blah blah blah, blah 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 is a, like my favorite example is a Turing machine as a quintuple, which has always struck me as being, just horrendously structured. And it's like, you could say, okay, well, fair enough. It is a quintuple in some sense, but I wouldn't have said it that way. I would have said a Turing machine has this tape and it has these things on it. It has this head, kind of building up this idea of what a Turing machine is, rather than just boom, a Turing machine is a quintuple. But people, who like pure mathematics like this kind of a Turing machine is a quintuple, I think. And again, here, if I'm to criticize this, it's this is a very structured statement. This is what it is. And as a refresher, that's clearly a good thing. As a, why would I write this down? Why would I write this? If I'm just coming to this from nothing, it's like, okay, that's nice. Why do I write that? Why don't I write sine of x? Why is that not here? Well, that happens to be FM synthesis, but what, and when I look at this series, it's like, okay, then I start getting even more confused. It's like, well, guess what? I wonder whether that series converges, but that was what Cantor asked. It led to transfinite numbers and everything else. But what is my point? I guess I'm, again, everybody has a different style, but to me, it's useful to see this very practical, this is an example of a Fourier series, and this is roughly what it does, because now I kind of know that what I'm trying to do is approximate some function.
So Stephen, the part of the bad news here is that your reaction to this particular computational exposition essay, whatever, is similar to the ones that other people have written. So I think you're in the situation where you have not yet found a single case where you are happy with the way this has been done.
Well, you're probably right. And I mean, there was one that I wrote as a sample, which I'm probably also not happy with. So let me critique my own example.
So that's very useful information, but then the natural follow-up from that is, how do we come up with one that you are happy with?
Let's find, does somebody know where the, okay, so I had this one from 2017.
So I have a potential suggestion. So it seems like Stephen is not opposed to the content that you have, Eric, but that it starts relatively technical and then comes to the examples. And for Fourier series, this is what the Fourier series is. There's nothing to be said. There's no discussion. There's no other possibility. But what about if one would slightly invert it and say, what kind of function can I build just from sine and cos? Make a manipulate with literally 100 sliders or points that you can move around, and always show that you can make a good approximation and then turn it around.
Yeah, that's kind of the computational, where you're exploring computationally in order to motivate something that might actually be true.
Saying basically you can approximate any function as it seems, so let's really do this.
That's interesting. I mean, okay, let's critique one that I wrote a while ago, 4 years ago or something now. So,
can you make it a little bit bigger?
Yep. Okay, I mean, I think I wrote this very quickly, and I think it's probably bad for many different reasons, but let's just look at it and we can all tear it apart. Okay, so first point is, it's an important result in statistics. Okay. Okay, I mean, I don't know whether we you can argue about is that it seems useful to me to say that. So what is the analogous statement for Fourier series? See, this is way more technical. Fourier series are a way of writing, periodic functions or something as sums of sines and cosines. By the way, when you say sine and cosine terms, you're not even telling me, I'm thinking about sine square root of 2x, but you don't mean that. What is a term? I don't know what a term is.
Well,
It's
it's
not
kind of hard to
self-evident
have.
that-
I need the equation to say what term is, and without spending a whole paragraph without the equation, it's hard to do. So I see what you're saying, but
No, I get it, but I think what you want to say is something like writing a function, an arbitrary function, as a sum of sine functions. Fourier series are a way of writing any function, any periodic function, as a sum of sine functions, sine and cosine functions, whatever. You know, that will be a good preamble statement, so you know roughly where you're going. Then this is useful because, or something, or this is and the fact, the mechanics of how it works, that there's orthogonality between different functions, that to me is plumbing about how it works, not what it is. Because, you know, the fact that, oh, well, we're going to do it in terms of Chebyshev functions, oh, they have a different weighting, blah, 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 would be like, you know, then the question is, how do I write this in terms of a sum of Chebyshev functions? The fact that my mechanics for, you know, generating that series uses a different, you know, way of extracting the terms is a different story. But I mean, let's tear apart my effort over here. Okay, so I mean, my effort here is sort of the experimental. Okay. I mean, again, please, criticism, because this so far looks okay to me. I mean, I would change this to code text, but that's a micro detail of the modern thing that we didn't have in 2017.
well, you assume someone knows what a normal distribution is. Is that safe to assume?
No.
Depends
no,
on
it's
who
not.
the audience is.
No, it's not. It's not. That's a good point. This probably should say a normal paren Gaussian
Bell curve.
a normal, you know, so this would probably be a better version.
Bell curve,
Bell
I would have
curve.
heard of.
Yeah, so if you say that, that would probably be a better way to do it. Let me just say this in a different place so I don't confuse this. I agree, that's a good change, because that way, that gives a sort of, by putting it in parens and quotes, you're kind of, right? I mean, yeah, it's a good change. Okay, but I mean, again, let's tear this apart.
For example, for a student, does it matter why you started with 1,000? What if we start with lower number? Does it make any difference?
They can try it. We're about to try 1,000. We're going to try 100,000 again. The reason I didn't start with a lower number is because it's like the carrying case problem, right? If that number is instead 100, right? What the heck am I supposed to learn from that picture? I don't know what that.
Okay,
What's the dip? Why two of them? What's the dip? Why do you need both? Does the result change? Isn't the central limit theorem true in both cases? You can just see it better with.
The reason I'm saying I'm using 1,000 and 100,000 because I'm showing that it gets flatter by the time you get to 100,000.
Here, one thing that I would confuse me is what is the relation of the number of bins? If you make 100,000 bin, it doesn't look flat at all.
Okay, you're in a carrying case. I'm referring to this as the carrying case problem, right? What is it that you're supposed to notice here? Good question.
And I noticed that kind of by clever bin size selection, it looks flat.
You're right. You're right. Now, would people actually notice that or not? I don't know. I mean, again, the problem is, it's like, here's a thing you get when people write documentation. Okay, people say, you didn't say the important thing in the documentation. You should have said first, like your Fourier series thing, this point about shifted Fourier series. You should have said that first. Okay, so you go around, you talk to other people, and eventually they everybody says you should have said this thing first. And pretty soon you've got 50 things you should say first. And guess what? That doesn't work. There's only one thing you say first. So it's this challenge of what can you elide while not having people get confused. And, yes, I think you've got to pick your poison. You see, if you do the same number of bins, it isn't going to work. And the whole point is we're not trying to give a sense, we're trying to give the sense, which I'm cheating on here. Okay, let's be realistic. I'm cheating about the fact that it looks flatter when there are 100,000 bins. And the question is that cheat okay, or is that my complaint about the electromagnetism book, where everything that's done is a cheat?
No, I think actually, if you keep the number of bins, it becomes more visible to your point. It's more emphasized.
Well, fair enough. Okay, but then the cost of that is that I have to, like, let's say here, I say 0.1 or something, and then I would say here, 0.1. But then, okay, that's kind of nice. But then I've got to, but see, I'm not even sure this is my point, that it gets flatter. Okay, so
but this is what you explicitly spell out. So
no, I know. But whether that's necessary. So Craig made the point. I would show a Gaussian earlier. I mean, maybe you're right. It might be. I don't disagree that that's but on the other hand, there is a certain value to the drama of something showing, appearing. I mean, that has, and the problem is if one's going to give it, I mean, one could say at the very beginning, a bell curve distribution. I mean, if this wasn't in the form of an abstract, I would say kind of like this, where at least you show, whatever, where I'm saying, and this is another question about how we do this, because I'm not sure what the right thing to do is. Okay, now I say like this, I fold that up. And I have to say, in the time since I wrote this particular piece, I have done more and more of my writing of kind of expositional stuff for the physics project and so on, where what I found pretty useful is you just give a result like this, and you want to know what the code is, just open it up or use click to copy. So I mean, that's a question, is to what extent can these essays be things where you show a result here, where you have to open the code explicitly, and to what extent is it kind of visible code? Somebody's asking what was actually in John von Neumann's case in the anecdote. It's a Geiger counter. It was a Geiger counter, radiation detector. In any case, yeah, I don't disagree that this is it's rather long in the tooth here. It's an awful lot.
The 10 seems very metrically decimal centered to me here.
Well, this is another one of these arguments about, oh, I see what you're saying. But look, if I'd chosen, Michael, what number would you have chosen there?
11.
See, I don't like that, because by saying 11,
always wanted this for the base.
What's that?
Lagrange always wanted 11 as the base of the decimal system.
What a nutcase! Did he also want to? Was he also arguing for a prime number of hours in the day or something? Why did he want that, Michael?
He wanted something in the order of 10, which he agreed was useful, but it was the nearest that wasn't divisible near 10.
Why did he want something not divisible?
Because he wanted to go away from this old Babylonian 2 times, 3 times 5. He wanted something holistic, one piece.
Great. Why? I mean, isn't it useful to be able to subdivide the units? I don't know. Anyway, that's interesting. I didn't know that piece of history, but the reason I wouldn't do that, okay, is the question is, what's the significance of that 10, right? And you might say, I mean, if I said this finds the mean of 13 random numbers, to me, that raises more questions than it answers. Like 10, okay, you're just sort of showing a bunch of numbers. Whereas 13, it's like, why is it 13? Is there something special about it being a prime? Is there, whatever? I mean, that would be my objection to that. I don't know. What do you, I mean, we're all, we're experienced expositors of things. So I'm curious about your thinking here, because I would never consider putting 11 there. Michael,
the 10 just, I have nothing against the 10, but you used 100, 10,000, and now there is a 10 in a spot that's unrelated to this round numbers that you used earlier. But it gives me the feeling there's a relation.
No, it's an absolutely fair criticism, right? So how does one deal with that? Oh, by the way, the reason that I'm making this list of 10 random numbers is to show people, before we go into histograms, roughly what on earth are we actually talking about here? Yeah, I mean, look, honestly, if we could get away with 5, I would use 5 here, because that's another kind of reasonable number that isn't a 10-ish number. I would consider using 20, but I wouldn't consider using a non-round number. Would 20 make you happier?
Yeah, actually, yes.
You're probably right. I mean, that's a good, and 20 is just fine here. Oh God, yeah, okay. Your criticism is very valid on this line, right? That's confusing. I agree with you. And okay, fine. And then maybe here, see, okay, that's fine. So that's okay. I mean, I claim that comments like that are useful, right? In other words, to make people, to highlight for people, look, it's not flat, as opposed to the distribution of the numbers themselves, which is flat. The distribution of the means of collections of numbers is not flat. And here we're kind of running into various issues about oh, okay, see here, gosh, see here, what I'm doing is I'm trying to explain up here, the thing that I was pushing back on here is I don't want to have to explain what that brace point 1 is. And again, that's one of these, that's sort of the inverse carrying case problem of you've added a bunch of stuff here. What is that extra stuff? Oh my gosh, I can understand histogram of random real 1,000 because I just saw random real 10 here. But what's that, what's that brace point 1? That's something weird. That's like the epilogue thing that we saw earlier. Well, anyway, I mean, I think, look, it's, I mean, I don't know, maybe this is just me, but to me, I find this kind of sort of, I would get much more motivated.
Yeah.
But go ahead.
In between, after your first experiment and before the normal distribution, I would now like to see, say, a transformed distribution with 2, 3, 4, 5, 6 up to 20 and see how it really approaches a Gaussian. Because right now I have no idea if
that
this
would be
is
a good thing to
trick or if this is reality.
Yes, I agree. And what I did here, which is sort of okay, is I don't know what this well, I'm looking at other distributions for the individual objects, and that's probably not the best way to get it, but that was a way to get it. And I think that's useful. But I agree with you. Before that, one should have the sequence. One should just have the table of results. I agree. That makes good sense, and see the limit happen. And then the next big result is it doesn't matter what the underlying distribution is. And I would actually break that off as a separate section. Because although the central limit theorem is all about the fact that it doesn't matter what the underlying distribution is, in a sense, the first step is just sort of, finding the Gauss, finding the normal distribution or something. And then the next thing is it doesn't matter what the underlying structure, what the underlying distribution is, you'll always get the normal distribution.
Stephen, to what extent we should care about labeling, this visualization? Like, as they are, is it good? Or like, we should add more content there to help the reader?
Well, I mean, I think that it helps to have this be explicitly a, code text thing. So at least you have some anchor for what's going on here. If you just look at this picture, you say, that's a cool picture. What is it? I mean, that's unfortunately a little bit, down in the weeds. But I mean, I tend to think, I do not think it should have a plot label.
I think one of the motivations, so some people get motivated of what you can do with something. One, you can be motivated by sort of exploring and discovering a result. But the fact that they converge to normal means that one can assume normality for a lot of things. That means so much simpler.
I know. So that would be a good thing to have at the end here.
Right. And the other thing at the end is like, it doesn't converge to normal in general.
I know. Okay, so these are pretty nice pictures. Okay, so I did exactly that, where the normal distribution appears, except I didn't finish it. And I was going to talk about error distribution, some blood levels, but not all. Okay, here's a good example of where that's the distribution of lengths of words, which is not a normal distribution. Not everything is. And find some data, show some that are, show some that aren't. I agree. I think it might also
be sums. The sums can converge to a stable distribution. They can converge to a distribution that's not normal.
But what I would be more concerned here is that not immediately the simple thing goes to normal distribution, but generically it goes to f of normal distribution. Because like string length, it sounds natural, but it really isn't. It might well be log of string length.
Mm-hmm.
There's somebody who goes to a normal distribution frequently.
See, we've got.
They take file
sizes. I see Craig making comments here. You see, this is there are too many experts here about about exposition for these things. Let's see. It's more visually intuitive if you start with something with non-zero mean. That's interesting. That's a good point. I mean, and again, okay. So, when you do one of these expositions, there will be, and, Michael and I keep on, and others here keep on coming up with, just think about plotting this thing. Just think about plotting that thing. Often I've had, this is my, what are they called in sports? The money shot or something, or whatever it is. I don't know what no, maybe that's photography. I don't know, but the really cool particular visualization that kind of is the top visualization, so to speak. And to my mind, I sort of pride myself on usually being able to figure out what that is, and that's a useful thing to think about. Is there some visualization that you are aiming towards, that you need to kind of build up to, and then some visualization where once somebody sees it, they're like, oh, I get it. I'm not sure what point I was really making there, but I mean, it's kind of fun to see that there are these cases where, as you make the sums over more and more numbers, you get something. It goes through these weird shapes and then ends up as a Gaussian. And I admit that, yeah. Well, let's see. What else are we going to achieve here? I'm really late for something else. I've been Actually, this is a pretty decent picture. What is our objective here? Our objective is, okay, so first point is, I think it is super challenging to write expositions where you don't understand fairly far ahead of the actual exposition you're trying to write.
I
mean,
absolutely agree.
You
shouldn't write one if you don't
Yeah,
understand.
it's worse to write it in such cases. It
Yeah,
will be a muddle, and it will not do our product or our people credit.
right. I mean, honestly, I've gotten better over the years at being able to get the distance between, the limit of my understanding and what I'm explaining to be slightly shorter. But it takes, I think it takes. I don't know how perfectly I do it, but it takes a lot of self-awareness of when you are stepping on something that you really don't understand, and how you avoid that. Which is to say, okay, so another question is, and this is something, when do people who are now, it's a paradox, right? Because on the one hand, you say you have to understand it very well. On the other hand, by the time you understand it very well, you're in the weeds. It's like I've worked with people in Roger's team many times where it's like, there's an example and they're like, oh, of course, it's this example. And it's, it's got unbelievable amounts of hair in it, so to speak. And to them, they don't even notice it because they're so steeped in that particular area. And it takes real effort to say, what's the point? What can we get rid of here? What actually matters? What doesn't? So, I mean, on the one hand, it's important to know the material. On the other hand, you have to kind of back away from that and say, what's the minimal thing that I can get away with talking about?
So in a sense, expert writes it, non-experts reviews it.
That's a good thing to do. If you can have you see, the problem with non-experts, okay? The problem is this, that people, they have to be obnoxious non-experts like me who have sufficient self-confidence that I don't really, to say I don't understand that is not something that bothers me, so to speak. I'm well aware that there are a great many things that I don't understand. And the trouble is that a lot of people, if you say review this, if they don't, I mean, this is a classic problem that we don't have around our company as much as many people have. That which you don't understand, you always assume to be true. I mean, arguably, it's a problem in the world in general. People have a habit of, if they don't understand something and somebody is telling them I'm the expert and this is how it works, and they don't understand it, it's like they say, oh, it must be true. And I know, my late friend Dick Feynman was very big on there are no experts, although his version of that was a little different than my version of it, which would be, I'm arrogant enough to believe that if I can't understand it, then I don't believe it, so to speak. But that doesn't mean that but yet, what am I trying to say? I think it is non-trivial to have non-experts review it unless they are in a mindset where they fully believe that they should be able, where they never take the point of view that if they don't understand it, it's their problem type thing. Am I making sense? I mean, so in other words, you can take the point of view, I don't understand that, and it's my problem because I'm just too clueless to understand it. Or you can take to the point of view, if I don't understand it, I'm going to push, I'm going to push, I'm going to push, I'm going to ask, explain. And if I really just don't understand it, it's a problem with the thing that's being explained, not it's a problem with me. And I don't know, it's hard to find non-expert reviewers who have that point of view.
But I think as it was said here many times, it's important to start these essays by what it is and why we care. And I think that part should obviously anyone understand. And then at that point, they would just know whether they want to carry on with how to do it. And how to do it can be done in different ways. That is very subjective to the way that the author is used to writing or has learned the topic himself and so forth. And probably by the time you're committed to learn, however it's written, the how we do it part, you'll probably try your best to get it through.
Shadi, I think it's important. The thing to understand is, the style of writing that, Eric did in Math World, that Wikipedia has done and so on, this direct, just tell it go say what's true, and don't, I mean, like for example, a bunch of writing that I do, it's like sometimes it gets really complicated. So for example, here's an issue. If it gets complicated, what do you do? And one thing I tend to do is I tend to say, it's a subtle point that blah, 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 blah. In other words, you're signaling this is getting complicated. And rather than you just dive right into it and somebody says, oh my God, I didn't understand that. This is getting way too complicated. At least if you signal this is getting complicated, then, then there's a chance that people can put up their, wait a minute, I have to go a bit slower. I'm not going to understand this as quickly, and get it, rather than just they barrel right through it and they say, oh my gosh, I didn't understand that. I mean, I think that, I do think, look, the question of who we're writing these things for, the interesting thing about MathWorld/Wikipedia has been that although, like in the math area, like Wikipedia has gotten too complicated in many cases, because I think it's gotten too much infected by essentially pure mathematicians writing for pure mathematicians. Whereas, I think if we can write it, I mean, I would like to claim that there's lots of writing that has the property that anybody can understand it, although not everybody will care about it. I mean, I don't know what, but I mean, Shadi, your point of say up front why one cares. Look, I'll tell you, when I write things, and obviously I write lots of stuff, like, I was writing, okay, let's bring up, we can criticize something of mine again for just a second here. Let's just pull something up here. Okay, like this was a thing I just wrote. How inevitable is the concept of numbers? Okay, so if we look at some section here, every section, there is at least an attempt to frame the thing in like, what's the point? I don't know whether that's a good one, but let's try again for one of these. Okay, I mean, again, I try to give these kind of introductory blurbs that are like saying what's the point of that section, so to speak. Yeah, I mean, again, each one of these probably took some effort. I know they probably didn't take very many minutes, but to what's the point of this section? Why do we use numbers so much? Is it something about the world, or is it something about us? Okay, at least you know what the question is there, I would claim.
Yeah, I agree.
And again, here, whatever their role in science, technology, society, one place where numbers seem fundamentally central is mathematics. Again, yeah, I mean, this is a good argument for, now I know what the point is of this section. I may or may not care about it, but I know what the point is. I will tell you, when I write these things, I usually, sometimes I nail these intro paragraphs very quickly. Sometimes I noodle for 5 minutes or 10 minutes or something, and I have many versions of them where they're considerably more complicated, and eventually they get simpler, and eventually they're fairly direct. I mean, I don't know what else is there? Another one here. Yeah, okay. So again, it's like, how do you start this section, right? And you kind of have to say something that's somewhat hard-hitting and somewhat, positioning for what the heck you're going to do. Anyway, I mean, I think I agree that it's, what you say first is important. And we've tried to do that in the introductions to guide pages and things like this. I mean, obviously here, this is in terms of writing, this is what I think they teach the kids is called a hook. It's like, what do you do? What do you write to get people to go on reading, so to speak? And usually in times when I have to say, usually in terms of making those hooks, when I've ever explained stuff to people And when I explain something to people and people just look sort of blank and like, I don't care, eventually I might find a hook where they say, oh, okay, that seems interesting. That's probably a good sign that that should be the very beginning of the essay type thing. I mean, obviously this is not an expositional essay. This is a different kind of essay. Anyway, okay. Next steps here, and we should, Hans is commenting that should have a link to the word random. Yeah, I mean, you see, this is where things get complicated. It's like, yes, I could write and have written hundreds of pages on what the meaning of the word random is. But you can't say everything first. And you have to assume people, okay, at a very meta-philosophical level, the very fact that we're writing in English, so to speak, we are assuming, we are leveraging, we built a tower of understanding represented by the words in English. And we are leveraging that understanding by the things that we're, if we didn't have the English words, we wouldn't have anything. We're leveraging that understanding. We have to assume people have sort of a rough intuitive sense of what random means, even if they don't understand, Chaitin Kolmogorov algorithmic complexity, this, that, or the other, or von Mises theory of randomness, or all these kinds of things. We got to assume, just like we use an English word, we've got to assume that people get something out of that. Now, by the way, extending that discussion, when we write pieces of computational language, the question is, what level, this is another good question of audience, what level of understanding? So I would like to make the claim that, well, if I get rid of that point 1, which I don't like very much, I don't like it just because it's an extra piece of hair in this input. I would like to make the claim that there's a decent chance. Okay, so one thing with this which is going to help, I think, a lot, is the new formatting. Which, have you guys seen this? Maybe, I don't know if anybody can pull it up. Jeremy's new formatting of code. Have you seen that stuff? Let me just bring that up if I can. Anybody know what I'm talking about here?
Not me.
Well, I certainly do, but that.
Do you know what? Yeah, okay, right.
Only because I'm part of those conversations.
Do you happen to know? Here we go.
I don't have it handy.
Okay, this is not a very good example, but the idea is to make code. One of the goals is to make, math is pleasant to read in a document. It kind of looks stylish. Code has a habit of not looking so stylish. The question is, how do we avoid that? And so we've been experimenting with these things like graying down the kind of the infrastructure operators and things like that. I think we can solve the problem of making it kind of easy to read this. Like I read this like I read words, histogram, random, real. If I gray down these operators a bit, then what I'm seeing is something that is as unforbidding as as a piece of English text, so to speak. And that to me is an important goal. Yeah, right. So let's see. Okay, Craig is commenting, the fact that paragraphs are short makes it less daunting, which is probably a good rule for essays. I agree with you. The code should be short, the paragraphs should be short. And I know I have to go here. And Erin is commenting that it'd be interesting to take a paper from archive and see how to make it more readable. Yes, there's unbelievably low-hanging fruit. Sometimes they're good, but sometimes it's like, oh my gosh, why did you explain that third when you should have explained that first? Why did you get to the point only at the end of the, in a sense, what you learn, as you try and look at technical papers in different fields, and it's different in different fields, you learn the kind of the formula for where do you actually go to find out what they're talking about, because it's often not the main flow of the paper. You'll go to, I often read the conclusions section first in many kinds of papers, because that's where they finally loosened up to the point where they're not so, tangled up in their own definitions that they can't say anything, and where you get some sort of intuitive description of, we figured out this and this and this, and then you can go back and say, now I don't really believe you, I want to know the details, but it will be enough. And you know, it's what abstracts are supposed to do. But I think sometimes abstracts are good. I mean, I've noticed, because I've been writing abstracts for things of mine recently, I have a terrible habit of making them sound formulaic and academic, which makes them less, you know, they're not as flowing as the things one might write, you know, just sort of, here's what the point is, so to speak. Anyway, yeah, I mean, look, this is years ago, Andre probably remembers this at least, we used to have, for technical writers at the company, we used to have a list of some principles of technical writing, of which the 0th one was, you've got to understand what you're writing about. I wonder whether that description is still around somewhere. But yeah, I mean, so look, this question, structurally, how do we do this? You know, I think it is necessary that people who are writing these are real experts. It is also very useful if there is a reviewer who can play the fool, so to speak, and is prepared to do that, and is not going to have the point of view, if they don't understand it, then it's that they're clueless type thing. Yeah, I mean, so Shadi, I think in your efforts, you know, we have to develop that kind of pattern of who writes, who comments on it, who complains about the fact that they can't understand it. I mean, Roger, I'm sure you're doing this a whole bunch with primary documentation, of cleaning it up like that. Is that a true statement?
Yeah, absolutely, a lot.
You see, you and I both end up being pretty good at playing the fool, so to speak, yeah. I suspect. I mean, in other words,
but the other thing that I have learned is that, well, people learn, I mean, at least to a certain level. Let's say that there's a book style, okay? We know several series of books that have a style, a very direct style, just like Eric established a style for Math World and so on. And we have a style that we do our documentation in.
Absolutely. It helps people a lot to have that very structured thing.
Right, there's a lot of things to look at. There's a lot of problems solved, and occasionally not solved, right? But then we have to go back and sort of get it.
Well, right, and the question then is, if there is a structure, somebody says, but I need to make an exception, right? And, you know, usually the best answer is no. Because, you know, usually it's like, well, just rethink how you're doing it so it fits. Sorry, you know, everything has to be less than a line long. Reword it, break it into 2 pieces, you know, rather than, oh, well, we can make an exception here, because the exception is a slippery slope that leads to something completely different in the end.
Exactly. But people need a bunch of sort of practical tricks. And the way you pick up a lot of practical tricks is by reading or seeing other, you know, sometimes.
No, I agree. It's like the famous encyclopedist trick, you know, where they write, it is said that, blah, 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 which basically means there's a controversial fact, which, you know, some people say and some people say it isn't true, or we really have no good evidence for this, but it is said that, you know, is a convenient kind of way to present something. In fact, I notice I'm sure I did that in this essay. It's said that there are human languages. Now, you know, behind that statement was me doing a bunch of research about whether that was really true or not. And it's complicated. And so the best I could do with it said that, because I didn't want to get into the whole, you know, oh, well, there are these anumeric languages and there are these, you know, Western influences on anumeric languages, blah, 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 blah. You know, that's just sinking into the mud. But yes, I agree, Roger, that is a good thing to have a family of those kinds of tricks. I think we need to do another one of these discussions. I think this is useful. I think maybe what we should do next time is to actually enumerate some of these principles, like, you know, when we are structuring, and you know, we don't really have a great structure. You know, this was my attempt to make a structure for a computational essay, and, you know, and then people kept on not following it, so to speak. And it's either is a structure that's going to work or it isn't a structure that's going to work. And that, you know, is something that we should determine. I mean, like here, this doesn't follow that structure. It doesn't have an intro thing, you know, so it loses at that level. And again, it doesn't have, no, you know, look, there was a structure, there was a style here. The style is, which is the EIWL style, There's a paragraph that explains things. Then there's a caption to a piece of computational language. And I think that's a pretty good scheme. We don't have these explainer paragraphs in documentation right now. And
I think a little teaser of the result on the top as well, because some of these may get very long.
that's a good idea. Yeah, that's a good idea. I
Sorry,
agree.
Stephen, I got to run.
Okay.
My
Thank you,
services as a bus are needed. Thank you all very much. I guess I'll talk to you again on another occasion in the near future.
Sounds good.
Bye.
Eric. No, but look, so I'm going to complain about this, right? It's like, we've got a style, this isn't following it. And, you know, again, the style is there's explanatory text, there's a caption that ends with a colon, then there's a piece of code. And that's, you know, that's the thing. Now you could rewrite this easily enough. You know, it needs positioning statement. I mean, look, why don't we just take this form and try and reframe some things in this form? And, you know, now one thing, maybe what we want to add. So let me just remind you, and again, we're so over time here. I'm going to remind you about one other thing, okay, about exposition, which is the EIWL effort. Okay, so one of the things that was in EIWL, and again, this is the stuff we have to invent. Shadi in particular, this is sort of for you. I mean, if I look at EIWL here, I've got the main text, which is very much the paragraph caption code, blah, 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 blah. Okay, now what I invented for this was this vocabulary section. I don't know how successful that's been. That's sort of a summary exercises. Okay, that was weird, but okay. Q&A was another important section, and then tech notes.
Mm-hmm.
Okay, so the point of tech notes is, you know, one thing you might do as you're writing your main text is like, you keep on looking over your shoulders saying, but what about an expert? They're going to tell me this isn't right. Well, then you can have something like tech notes at the end, which is, okay, you're an expert. Look, you know, the author was not as clueless as you thought. And when you say, are they really talking about this? Then, you know, that is telling them that, so to speak. And similarly, this Q&A, it's like, you know, answer the obvious questions. We haven't done this in documentation. We could consider it. I don't know. Don't know if it's a good idea. But I found this super helpful in writing the IWL book, because there were just so many things where, okay, color negation, right? So I probably have a thing up here that color negate, quotes, negates a color, giving the complementary color. Okay, so you might reasonably ask, what on earth does that really mean? You know, somebody, the expert is looking over your shoulder. Shadi, Roger, other people here know perfectly well that color negation depends on the color space, right? So the expert looking over your shoulder is going to say, what are you talking about? But you don't have to worry about that, because you can, you know, that's enough for the typical person. You can go down to the tech notes where it's like, okay, what do they mean by color negation? Well, you know, whatever, here we go. Okay, are there ways to specify colors other than RGB? Okay, there, I mean, that's again, you know, some kind of explanatory thing. So I don't know. I mean, my point is, for these essays, we have to, expositions, we have to invent some devices like this. And that's, you know, we've been very successful in documentation. It's lasted 30 something years. You know, the devices that we have for documentation, you know, there are different devices to be invented for these other things. This is an example, you know, see what seems to fit. I mean, here, I invented these devices because I was getting stuck. I was like, I don't know what to do about this. I've got a technical point. Do I put a footnote? You know, how does this work? All right. And people are commenting here that we should have a style guide online, and I agree. If we get this properly straightened out, that we should codify it properly. I agree, and I think it'd be useful. We do have some stuff for people writing Padlet documentation, don't we? People using the new documentation tools. Do we have that, Andre? Well, I think we'd certainly implicitly in the tools, we'd written some of that stuff.
Yeah, but I don't know how much of it is absolutely there waiting for a Padlet update.
Fair enough. Okay, we need to go to this other meeting. I apologize to.
And you can bring it up in the meeting you have to go to next.
Yes, I understand. All right. Well, thanks, and thanks to folks on the live stream. And we will continue into another one of these because I think this is going to be useful. And next time, the deliverables from the next meeting will be the actual, and people can come with a set of suggestions for what our sort of style guide is. That will be very helpful. And talking about what our types of documents are going to be and what the style guides are for those types of documents.
Okay.
Okay. All right. See you guys soon.